అంటే సర్లేదు.
అది మీకు పాతది అయిపోయింది.
అయింది.
హలో
మేడం
చెప్పండి.
అది నాకు మీ ఇంటి లొకేషన్ అది
Good evening, everyone. Let's wait for 5 more minutes and start the session. Already, Venkat Subbareddy sir is in the Zoom meet. So by 6:10, let's start the section.
Good evening, everyone. A warm welcome to all the participants to Day 4 of our 5D National Level Professional Development Program on Quantum Computing, organized by the Department of CSE, CYS, DS, and AIDS, VNRVJIET in association with Blackbucks Education Private Limited. Over the last 3 days, we have explored the fascinating foundations of quantum computing with Dr. Swati Mummadi, covering qubits, superposition, entanglement, quantum noise, error mitigation, and quantum machine learning applications. Each session has built a strong conceptual and practical base for today's advanced discussion. It is my great pleasure to introduce today's distinguished resource person, Professor Dr. P. Venkata Subba Reddy, Associate Professor, Department of Computer Science and Engineering, NIT Warangal. Dr. Subba Reddy holds a PhD from NIT Trichy and is widely recognized for his expertise in quantum Fourier transformation and algorithmic graph theory. His research focuses on developing efficient algorithmic solutions to complex graph problems and quantum inspired optimization techniques. He has published extensively in top tier journals including Theoretical Computer Science 2025 and Applied Soft Computing 2024, addressing the advanced topics like quadruple Roman domination and meta-heuristic methods for dominance problems. Beyond his research excellence, Dr. Subbareddy is a passionate educator and has conducted numerous faculty development programs on quantum computing, helping faculty and researchers simplify and internalize the abstract mathematical principles behind quantum algorithms. We are truly privileged to have him with us today to share his deep thoughts on algorithmic perspective in quantum computing, a session that promises to blend theory, mathematics, and real world quantum applications. Let us all extend a warm welcome to Professor Dr. P. Venkata Subba Reddy. Sir, the session is now over to you. Sir,
Sir, oh, you are in mute, sir.
looks like Sir is having some emergency call at the moment. Let's wait for a few minutes.
Actually, sir engaged in some emergency call. Dear participants, just wait for few more minutes. Sir will be back.
Really sorry for the delay. Sir has joined the class.
Sir, you can talk. Subhadip, sir.
Hello.
Yes, sir, we can hear you. You can
Oh,
continue.
okay. Thank you, madam. Thank you. I am sharing my screen, madam. You please tell me if it is. Is my screen visible, madam?
Yes, sir.
Okay. Okay. So first of all, I thank Blackbucks for giving me this opportunity to deliver a talk on QFT, and I am extremely sorry for the delay. Okay. So is my screen visible?
Yes, sir.
Okay. Okay. Thank you, madam. Thank you. And I request the participants to be. Madam, is it possible for the participants to unmute themselves and respond?
Actually, no, sir. You just
Yes,
ask a
sir.
question, sir. We will provide us. No issue.
Okay, ma'am. We'll try to keep it interactive. Then, okay, na? Okay.
Yes, sir.
You may allow, madam. Okay, no. If there is any disturbance, then we can. Okay.
Okay,
Okay,
sir.
sir.
Okay. Thank you.
We will.
Okay. So, this is the outline of my lecture. So, we talk about mainly quantum Fourier transform. To understand this, what are the things required? These are the things that are required. Okay. So, I will make it self-contained. If you have any doubts, you can interrupt me at any point of time and you can get your doubts clarified. Okay. And we make it the lecture interactive. Okay. Whenever I ask a question, if you know some answer for that, you may please unmute yourself and respond. Okay. So what is a row matrix? So we know that a row matrix is a matrix which contains only one row. This is the general form of row matrix. This matrix has only one row and n columns. N columns. For example, 257. Is it a row matrix? Is it a row matrix? Is 257 a row matrix?
Yes, sir. Yes, sir.
Yes.
No, sir.
Yes. Minus 3041. Is it a row matrix?
Yes, sir.
Yes. 6.
Yes, sir.
Yes. These are all examples for row matrix. Similarly, can you define what is a column matrix? So it is a matrix which contains only one column. So now 2570, is it a column matrix?
Yes, sir.
Yes, sir.
Yes. Minus 30, this is second one, is it a column matrix?
Yes, sir.
Yes, sir.
Yes. Third one, is it a column matrix?
Yes. Yes, sir.
It is row matrix as well as column matrix. It is satisfying conditions of both, no?
This is కలిపి వర్కింగ్ అంటాడు.
Okay. Now assume that I am talking about a system that is coin system, tossing a coin. So what are the outcomes? What are the outcomes? I may get heads or tails. Okay. Now we have tossed a coin and the coin has fallen on ground. Okay, no, it has fallen on ground. Once after that, we can see whether we have got heads or tails. No, is that correct? Now suppose we have got heads. We have got heads. Now, can we write what are the probabilities of getting heads and tails? Heads probability 1, tails probability 0. Is that correct? I am fixing order like this. First heads, second tails. Is that okay? Similarly, what is, for example, suppose we have got tails. Then how do we represent that? My order is same. Heads first, is tails next. This is the order I have fixed. Now, what is the matrix for what? How to represent tails?
0, 1.
0, 1. 0, 0, 1. Now, the same this is it of the form of a matrix? Is it a column matrix or not?
Yes, sir.
Okay, this column matrix only we write it as get heads. Now, what is get heads? Column matrix 1, 0. Now, tell me what is get tails? Column matrix 0, 1. Is that okay? Now, instead of heads tails, I am performing some experiment. I am talking about switch. Switch is either on state or off state. Okay. Now suppose I know that switch is on state. Okay, no, this is off state, this is on state. I know that this is off, this is on. Now this is the order I am following, off, on. Now if I know that switch is in off state, how do you represent it as a matrix?
0.
How do you represent it as a matrix?
0, 1.
0, 1 or 1, 0?
1, 0.
0.
No, 1, 0. I know that switch is in off state, off state probability is 1. Are you getting?
You said off 0 now, sir.
Switch is in off state now.
Yeah.
Then off place 1 should come, no? Switch is in on state. Switch is in on state. Then it is 0, 1. Now off state is nothing but 0 state. I can write it as get 0. On state is nothing but 1 state. I can write it as get 1. This is get 0, get 1. This we read it as get 0, get 1. This notation is known as direct notation. Okay. Is it clear now? What is get 0? What is get 1? Is it clear? What are the matrices for that?
Yes, sir.
Okay. Now this is very basic. ABCD is of this course. Now what is matrix for get 0? Can you tell me?
1, 0.
What is matrix for get 0?
1, 0.
1, 0. What is matrix for get 1?
0, 1.
0, 1.
Now we can talk about bra 0. This is bra 0. If all numbers in a matrix are real numbers, corresponding bra is nothing but its transpose.
Transpose.
Now what is transpose of 1, 0?
As a row matrix, 1, 0.
As a row matrix 1, 0. Thank you very much. What is transpose of 0, 1?
0, 1 as a row matrix.
Row matrix. Is it okay? Now can you calculate what is get 0, bra 0 product? What is get 0, bra 0 product?
1.
Get 0 is 1, 0. Bra 0 is 1, 0 row matrix. Now it is like a normal matrix multiplication. Can all of you do multiply and tell me what is the result?
1.
1,
Unit
sir.
vector.
1, sir.
Unit vector.
Now this matrix, what is the order? It is 2 by 1.
Not possible.
2 by 1.
2 by 1, 1
This is
and
1
2.
by 2. Result will
Unit
be 2 by 2 matrix, no?
Yes.
Unit vector, sir.
Not
This is
unit
normal
vector.
matrix multiplication. Normal matrix.
Yes.
1 into 1, 1. 1 into 0, 0. 0 into 1, 0. 0 into 0, 0. Is this okay?
Okay.
This is normal matrix multiplication. Normal matrix multiplication. I hope all of you remember what is how to multiply two matrices. If you do normal matrix multiplication, we will get this. Similarly, what is 0, 1? Get 0, get 1. Get 0 means 1, 0. Bra 1 means 0, 1. Again, multiply this. This is the way we need to multiply. Is that okay?
Okay.
Now, get 0, bra 0, get 1, bra 1. Notations clear at least?
Yes, sir. Yes, sir.
because these are basics. We will be using, okay, no, not only this lecture, any lecture on this course, okay, no, this you should never forget. Is it clear now? Ket 0, bro 0. Okay. Now these notations are due to Paul Dirac, and this notation is known as Dirac notation. Okay. Now, what does a qubit mean? So already some lectures have been completed as part of this course. What does qubit mean? So this general form of a qubit is alpha ket 0 plus beta ket 1. Now we know what is ket 0. Ket 0 is 1 0. What is ket 1? Ket 1 is 0 1. So it is written of the form alpha ket 0 plus beta ket 1, where alpha beta are complex numbers, and these are called probability amplitudes. Okay, now probability amplitudes. What is the main condition it has to satisfy? Mod alpha square plus mod beta square equals to 1. Okay, now I'll give you some example states. You tell me whether it is a qubit or not. What about ket 0? Is it a qubit or not?
Yes, sir.
Why ket 0 is a qubit? Ket 0 is what? 1 0. Now 1 0 I can write it as 1 into 1 0 plus 0 into 0 1. Is that correct? What is 1 0? 1 into ket 0 plus 0 into ket 1, where alpha is 1, beta is 0. What is the condition it has to satisfy? Mod alpha square plus mod beta square is 1. Is the condition satisfied here?
Yes.
Mod 1 square plus mod 0 square is 1. Yes. Hence it is a qubit. Okay. What about this one? Ket 1, is it a qubit or not? If it is a qubit, you should be able to write in this form. Is ket 1 a qubit or not?
Yes, sir, it is.
How to write it, sir? Ket 1 is 0 1. 0 1, can we write it as 0 0 plus 0 1? Do you agree? 0 plus 0 0, 0 plus 1 1. Correct now? This 0 0, I'll take 0 outside. Can we write it as 0 times 1 0? This 1 I will take outside. 0 1. This is alpha ket 0. Sorry, 0 ket 0 plus beta ket 1 form. Is that correct? Mod alpha square plus mod beta square. Alpha is 0, beta is 1. Mod alpha square plus mod beta square, if you calculate, you get 1. Is that correct? Is it correct or not? Is it a qubit or not?
Yes, sir.
What about this? Is it a qubit? Third one, is it a qubit?
Yes, sir.
Mod alpha is 1 by root 2, beta is
And
1
beta
by
is
root
1 by square root
1. What about fourth one? Is it a qubit?
Yes, sir. That is also beta is equal to minus 1 by square root 2.
If we take square, then it will be 1 now. Is that okay?
Yes, sir.
Okay. What about fifth one? Is it a qubit or not?
Sir, we are not getting the audio, sir.
Okay. No. I just asked whether is this a qubit or not. I thought you are working out. Is it okay now, sir? Can you hear me? Hello?
Yes, sir. You are audible, sir.
Okay. Is it a qubit or not? What is alpha here? 2 plus 2i by 3. What is mod alpha squared? If alpha is of the form
Yes, sir.
a plus bi, mod alpha square is given by mod a square plus mod b square. This you might have learned. Okay. What is a square? Mod a square 2 by 3 whole square. Mod b square again mod 2 by 3 square. 4 by 9 plus 4 by 9. It is 8 by 9. Is that okay? What is mod beta square?
1 by
Mod
3.
1 by 3 square 1 by 9. Now you tell me, is mod alpha square plus mod beta square, is it equals to 1?
1 by
Is it equals to 1?
yes, sir.
Yes, hence it is a qubit. What about sixth one? That is also qubit. That is also qubit. Next, now we are familiar with what is Dirac notation, qubit. What does qubit mean? Okay. Next one, we need to understand tensor product. Okay. No? We need to understand tensor product. Instead of directly looking at this formal definition, we will go with an example. Okay. Now you are given two matrices here. How to find tensor product? How to find tensor product of AB with CD? So ket psi tensor product symbol is this. Okay. Ket psi. What is tensor product? So we are given two matrices AB, tensor product CD. How to find this? We need to take first matrix as it is. I have taken first matrix. Next to each element of first matrix, you copy second matrix. Second matrix, first A, after that you copy CD. Second element B, again you copy CD. Is that okay? Is that okay? Now what is that you do is you multiply the terms A with C, then we get AC. A with D, AD. Next B with C, BC. B with D, BD. Is it clear? Is it clear? Is that clear?
Yes, sir.
Okay. Now, can you tell me, is this okay? What is tensor product of 1 by 4, 3 by 4 with 2 by 3, 1 by 3? 1 by 4, 3 by 4. Next to 1 by 4, you copy 2 by 3, 1 by 3. Here also 2 by 3, 1 by 3. You multiply terms and put it in the order. 1 by 4 into 2 by 3. Next to 1 by 4 into 1 by 3. 3 by 4 into 2 by 3. 3 by 4 into 1 by 3. Is this clear? Is it clear?
Yes, sir.
Yes, sir.
Okay. What is tensor product of this? Can you please do it? What is tensor product of this? What is tensor product? First matrix you write down. Next, against each element, you copy second matrix. Is that okay? Is that okay? Now what is that we need to do? V1 with W1 multiply, whatever result we get that. Next to V1 with W2, V1 with W3, next to V2 with W1. Is that okay? Is tensor product clear?
Yes, sir.
Okay. Now can you tell me what is tensor product of these two matrices? Actually, these are quantum states. What is tensor product of these two states? Alpha 1 We need to
alpha
copy
1
the
beta 1
alpha.
multiplied alpha 1 beta 2 multiplied by alpha 1 beta 3 and so on alpha 1 bk. Then alpha 2
Yeah, thank
b1
you.
alpha. Yes, sir.
Thank you very much.
Alpha 1 is multiplied by the column of b1 beta 1 beta 2 and so on bk. Then alpha 2 is also multiplied by beta 1 beta 2 beta and so on.
Yeah, thank you very much. Okay. Okay. Now all of you please calculate this. Now you know what is ket 0. Okay, what is the matrix for ket 0? 1 0, no? All of you calculate this. What is tensor product ket 0 tensor ket 0?
One zero zero zero.
1 0 0 0.
1 0 0 1 0 0.
So is this okay? First matrix as it is I have written. Against each element, second matrix I copied. Now finally what is that we get? Is that okay? Okay. This ket 0 tensor ket 0, we also write it as like this. Another way of writing is directly combining them without this. This way also we write. However we write, you should not have any confusion. All are referring to this matrix. Is that okay? Can you tell me what is ket 0 tensor ket 1? Ket 0 is 1 0. Ket 1 is 0 1. Can you please complete it?
0 1 0 0.
0 1 double.
0 1 0 0. Okay. These are other ways of writing this. Now tell me what is, similarly can you understand this? What is ket 1 0? Ket 1 tensor ket 0. If you multiply, finally you will get this. Ket 1 tensor ket 1. If you multiply, we will get this. This we can also write it like this. Whether this 4 tensor products, any doubt? Any doubt? Any doubt in this 4?
No, sir. No, sir.
Okay. Now can you please calculate what is ket 1 tensor ket 0 tensor ket 1?
Sir, associativity has to be known here.
First 2 we can calculate, no? First
Left
2 we
associative.
calculate.
Okay, okay. So left associative.
It is both sides actually. Okay, however you calculate, you get the same result. Like matrix multiplication type.
Okay, sir.
Now ket 1 tensor ket 0, this is the answer. Now what is this part? Already this part we calculated. Now what is the answer? What is the answer for that part? What is the answer?
0 0 1 0.
Already it is given above, no? 0 0 1 0. So this entire part is nothing but 0 0 1 0. So same thing I copied 0 0 1 0. Against each element I copied this second matrix. 1 0. Sorry.
Sir, 5 zeros.
Ket 1 is 0
0
1. Ket 1 is 0 1. Here it is mistake. Here it is correct. Okay. Is that okay? Now finally, can you please complete and tell me?
Sir,
what is
5
the answer?
zeros. 5 zeros 1 0 0.
Thank you very much, sir. If you complete, then you will get 5 zeros 1 0 0. Now this we can write without this symbol also. Without this symbol also we can write. By combining, we can also write it as like this. Is that okay?
Sir, is it 1 1 1?
Triple one. Ket 111. No. This is
101.
This is 101. No, 101.
Sir, yes, sir. That's what.
This is 101. Okay, this is 101. No, this is not. Next example that you are. Okay. This is 101. Okay, this is the change. Okay. Same thing, 101 only. Here we need to copy without that symbol. That's all. Now, can you tell me? Okay, you please try later. What is ket1 tensor ket1 tensor ket1? This is for assignment. Ket1 tensor ket1 tensor ket1. Okay. One question. Next, what is conjugate transpose of a matrix? We are given a matrix like this. What is its transpose? What is its transpose? What is B transpose? What is B transpose? 1 plus I, 3 plus 2I, 2 minus I, 4. Is this correct? This is B transpose. Now, what is conjugate transpose? Each element of the matrix we need to take conjugate, complex conjugate. What is complex? A plus IB is the element. Its complex conjugate is A minus IB. Is that okay? IB, BI, we write interchangeably. A plus BI, it is A minus BI. Now we have taken transpose. Then what is that we need to take? Conjugate of each element. What is conjugate of 4? 4 can be written as 4 plus I into 0. What is its conjugate transpose? 4 minus I into 0, which is same as 4. Real numbers conjugate is that number only. 4 conjugate is 4. What about 1 plus I? What is 1 plus I conjugate?
1 minus I.
1 minus I, thank you. What about 3 plus 2I?
3 minus 2I.
3 minus 2I. 2 minus I?
2 plus I.
2 plus I. Is that okay? This matrix, this is called B dagger. This is called conjugate transpose of given matrix. It is called conjugate transpose of given matrix. Is that okay? It is called conjugate transpose of given matrix.
Sir, how do you pronounce it, sir?
Conjugate transpose. B dagger, dagger.
Okay, okay, sir. Okay, sir.
B dagger. Okay. Now, what does unitary? All quantum operations are represented by unitary matrices. You must be knowing this by this time. So, what is unitary matrix? A square matrix is said to be unitary. A square matrix U is unitary if U times U dagger equals to U dagger times U equals to identity. How to check whether 1001 is identity unitary or not? Given matrix is 1001. This is U. What is U transpose? U transpose is 1001. What is U dagger? U dagger also 1001. Is there any doubt in this? U equal to 1001. U transpose is also 1001. U dagger is all numbers are real. So complex conjugate, if you take also no change. That's why 1001. Then what is that we need to do? U times U dagger. What is U? 1001 times U dagger. Again 1001. Result is again 1001. Is that correct? Similarly, other side also we can show. Hence, this matrix is unitary matrix. Similarly, this matrix is also we can show that it is unitary. This matrix is also unitary. This matrix also unitary. This matrix also unitary. This matrix is also unitary. That means all these matrices represent valid quantum operations. What is the name given to this matrix? This is called X gate, quantum X gate. What is the name given to this? This is called Hermod gate or Hermod operation. Okay. This is called phase gate. So each one has name also. At least these two I think you might be knowing these two. X-gate and Hermod gate. Is that okay? All quantum operations are represented by unitary matrices. When do you say that a matrix is unitary? If a matrix U is unitary, if U times U dagger equals to U dagger times U equals to identity. Okay. Now, this is unitary matrix. How many qubits this matrix takes as input? It is a 2 by 2 matrix. It is of the form 2 power 1 into 2 power 1. Hence, it takes 1 qubit as input. That's why all these matrices they represent single qubit operations. Hermod operation is single qubit operation. That means input to Hermod gate is 1 qubit. Input to X gate is 1 qubit. Are you following?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So if I am talking about 2, I want a gate which should operate on 2 qubits. What is the order of that matrix? What is the order of that matrix? It should operate on 2 qubits. It should be 2 square into 2 square. That means 4 by 4 matrix. If I want a gate or a quantum operation which operates on 3 qubits, it should be 2 power 3 into 2 power 3, 8 by 8 matrix. Is that okay? Okay. Now, as I mentioned, this matrix, this operation, this is called Hermod operation. This is the circuit diagram for this. If ket0 is given as input, then what is the state we get after applying Hermod gate? How to calculate that? Ket0 means we know that it is 1 0 1 0. Hermod gate we apply. So that means we need to apply Hermod on ket0. What is Hermod? Hermod on ket0. What is Hermod? This entire matrix. This entire matrix. Ket0 means 1 0. You multiply these two now. We will get 1 by root 2, 1 by root 2. 1 by root 2, 1 by root 2. This I can write it as 1 by root 2 0 plus 0 1 by root 2. Is that correct? Is that correct? 1 by root 2, 1 by root 2, we can write it this way, no? Now from first matrix, I will take 1 by root 2 outside. Then it will be 1 0. From second matrix, I will take 1 by root 2 outside. Then it will be 0 1. Then what is 1 0? It is ket0. What is 0 1? It is ket1. And this state is known as plus state. Is it okay? Is this clear? Hermod gate on ket0, it gives 1 by root 2 ket0 plus 1 by root 2 ket1. This state is also known as plus state. Is there any doubt? And this is known as, is it a linear combination of ket0 and ket1? Is it linear combination of ket0 and ket1? Whatever
Yes.
state we got, is it linear combination of ket0 and ket1? That linear combination only we call it as superposition. This is only we call it as superposition. Not only that, it is equal superposition. So Hermod gate, if you give ket0 as input, it puts both states 0 and 1 in equal superposition. That's what it is meaning. Okay. Both will get with probability 1 by 2, 1 by 2. Probability is this square. Okay. Now can you please tell me what is the answer here? Hermod on ket1. Hermod gate, if I give ket1 as input, what is the answer? What is the state we get here? Hermod gate, ket1 we are giving as input. What is the state we get? You write it. H means what is the matrix? 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. What is ket1? Ket1 means 0, 1. You multiply both over, no? Are you following or any doubt? Okay.
Yes, sir, we are following.
Okay, and this state is known as minus state. Okay, Hadamard on ket 0 is plus state, Hadamard on ket 1 is minus state. This is also equal superposition state. Measurement gives, see, alpha ket 0 plus beta ket 1. If I go for measurement, what is the probability of getting 0? Mod alpha square. What is the probability of getting 1? Mod beta square. Here is it correct? Probability of 0 is this. Probability of 1 is minus 1 by root 2 square. Is that okay? Okay. Now, the C naught, there is another gate called controlled NOT gate. Controlled NOT gate. What is quantum NOT gate? That is also called as X gate, no? X gate. X gate. So this control NOT is a 2-qubit gate. It is a 2-qubit gate. And if these are inputs, these are the outputs for that. That means if 0, 0 is given as input, we will get 0, 0 as output. 0, 1 is given as input, we will get 0, 1, 1, 0, 1, 1, 1, 1, 1, 0. How to understand this? So here, the first one is called control, this is called target. The first one is called control, this is target. If control is 1, then target is flipped. Target is flipped. Flipped means 0 becomes 1, 1 becomes 0. Now see, control is 0, so no change. As it is, we got. Control is 0, no change. Whatever input, same output we got. Control is 1. What happens? Target 0 becomes 1. 0 becomes 1. Control as it is. Controls are as it is. Targets only, they are changing. Is that okay? Is this okay? Control is 1. This one becomes 0. 1, 0 is the answer. First column and third column both are same as it is. Control as it is copied. Only target value is calculated differently. How to calculate this target value? Another way of calculating is, what is 0 XOR 0? What is 0 XOR 0?
0, sir.
0 XOR 1?
1, sir.
Wow. 1 XOR 1? 0.
0, sir.
1 XOR 0?
1, sir.
1. Okay. Now, you look at S column. Can you say that S column is obtained by applying P XOR Q? S is same as P XOR Q. Do you agree? S is same as P XOR Q.
Yes, sir. Yes, sir.
That's why this is a matrix form, because this is 2 by 2 qubit. No, that's why 2 square by 2 square. Okay. This is a matrix form. This is called control part. This is called target part. This is XOR symbol. XOR symbol. This is called control NOT gate. Now, can you tell me what is, if 0, 0 is given as input, what is the output? What is the output? What is the state here?
0 state.
0, 0 only. How to get that? If you know the matrix for this, this is a matrix. This is a matrix. How to write okay, control NOT matrix, how to write that? Any control operation, matrix writing is very easy. So first you put here identity matrix. Here you put matrix with all zeros. Matrix with all zeros. Here, if it is control NOT, control, after that, what is the actual operation? NOT operation. NOT means what is the matrix for NOT? 0, 1, 1, 0 is the matrix for NOT. No, it is called X gate. It is called X gate. So now here you put that corresponding gate. Gate or operation. Now you tell me, I means 1, 0, 0, 1. 0 means 4 zeros. Again 0 means 4 zeros. X, here it is control NOT. No, NOT means what? 0, 1, 1, 0. This is only matrix for C0. You can see here. Correct now? I 0, 0 X gate. Is that okay?
Yes, sir.
Now C0 on ket 0, 0. This is C naught. What is ket 0, 0? We have already calculated now what is ket 0, 0? 1 0 0. Starting of the lecture, we derived this now tensor product. This is the matrix. For ket 0, 0, this is the matrix. We directly use that. And after that, it is normal multiplication. We got again same thing. Again, same thing. In this case, what is the answer? In this case, what is the answer? In this case, what is the answer?
Is it 1 1, sir?
What is math? Now all of you should be able to write C naught matrix without seeing also. X gate, if you remember C naught, you should be able to write. Again, I repeat, I 0 0 X gate matrix. I means identity. Identity matrix means we know that it is 1 0 0 1. 0 means 0 matrix.
0 0.
Again 0 means 0 matrix. X means
C naught.
0 1 1 0. Is it clear? This is C naught matrix. Is that okay? Ket 1 0. What is matrix for ket 1 0?
1
What is matrix for ket? Okay. This is the matrix for ket 1 0. Okay. Now you simply multiply. What is the answer you expect? 1 0 should change it as control as it is. Target becomes 1 XOR 0. That means it should become 1 now. Answer should be ket 1 1. Is that okay? If first control bit is 1, target bit is changed. That means 0 becomes 1, 1 becomes 0. That we call it as flipped. Is that okay? Is that okay?
Yes, sir.
Is that okay? Now there is another gate called phase gate. Okay. So now we have X gate, Hermite gate, like that. This is phase gate. What does this gate do? Now can you calculate? If I give ket 0 as input, ket 0 as input to this gate, what happens? 1 0 0 e power I theta. Ket 0 is 1 0. If I multiply, what is that we get? What is that we get? Again 1 0. This is ket 0. Again I have got ket 0 only. If ket 0 is given input, ket 0 only we get. Once you know the matrix, after that it is only normal multiplication. Now what about ket 1? If I give ket 1 as input, what will happen? 0 1 0 0 e power I theta. Now what happens? 0 1 is the matrix for ket 1. What is the matrix? What is that we get? 1.
For I theta 1.
1 into 0 0. 1 0 into 0. This okay? No, this is 0, no? 0 e power I theta. Correct? E power I theta I can take outside. Then it will be 0 1. 0 1 is nothing but ket 1. E power I theta ket 1. Correct only, no?
Yes, yes.
How we got this in normal multiplication? Because already I have shown, I have not explicitly mentioned here. Is this okay? Ket 0 as it is, we get ket 0. Ket 1 will get e power I theta, this factor extra. Okay, now phase factor extra. Now can you tell me what is control version of this r theta gate? Control version of this gate? Control version of this operation? How to represent that? Control version of this operation. Already control not I explained, no? Can you tell me? I 0 0 this r theta I need to copy, no? What is I? I means 1 0 0 1. 0 means 4 zeros. Again 0 means 4 zeros. R theta means 1, 0, 0 e power I theta. Is that correct? Is that correct? That's all. That is our next gate. Okay, same matrix, no? You see here. This is I, 0, 0. This is R theta, no? Because we use this gate in our QFT. Okay. Is this okay? Control target. This is the notation. Now you tell me. Here what happens? Control is 0, 0, 0 is input. What is the output we get?
0.
Same output. If control is 0, no change in the output. Here also control is 0, simply we can copy as it is. Okay. Control is 1. Then what happens? Get 0, they apply that gate. If you apply get 0 to this gate, what is that we get? Again get 0 only. Is that okay?
Yes.
So that means what is the answer here? It is get 1. Here also get 0. Here what happens? Get 1 as it is we get. Because control is 1. Get 1, the gate is applied. This gate is applied. If we apply this gate, what is the answer? This we have already seen now. E power I theta get 1.
Yes, sir.
So finally, what is our observation? 0, 0 will be 0, 0 only. 0, 1 will be 0, 1 only. Get 1, 0 will be get 1, 0 only. Get 1, 1 becomes e power I theta times get 1, 1. That is the only change. This is this gate. Is that okay? For different theta values, we use this gate in our circuit, QFT circuit. Okay? Is it clear now whatever I have discussed so far?
Yes, sir.
Yes, sir.
Okay. Okay. Now, last gate which we use in our QFT circuit, it is swap operation. Swap means anyhow it is self-explanatory. What happens? Can you guess? Swap gate or swap operation. What happens? If we have 2 qubits, it interchanges that 2 qubits. It interchanges that 2 qubits. For example, this is first qubit, this is second qubit. After applying this swap operation, what happens? This qubits got interchanged, no? Is this correct? This has become first qubit. This has become second qubit. Is that correct? It simply swaps the qubit. 2 qubits, it changes the order. Now if 0, 0 is there, what is that we get? What is that we get after applying swap gate?
0, 0.
0, 0. If 0, 1 is there?
1, 0.
1, 0.
1, 0. If 1, 0 is there?
0,
1.
0, 1. 1, 1?
Same will get.
Same will get. Is that okay? This is the matrix and this is the representation of this. Okay, now this is the way we represent. Q1, Q2 inputs, Q2, Q1 outputs. Okay. This gate also we use in our QFT circuit. Okay. Okay. Now, okay, apply stop gate to this. What happens? 0, 0 becomes what? These are called Bell states. These are all entangled states. Okay. 0, 0, what happens? If I apply 0, 0, this will be 0, 0 only. 1, 1, if I apply, it is 1, 1. No change, same thing I get. Same state I get, no? What about here? What about here? Second state, if I apply? Swap gate to second state.
Same state, 5 minus.
Same state. Thank you, sir. Third gate.
Third gate is.
5 minus, sir. It will be converse.
You see
1
here,
0 and 0.
0 1 becomes 1 0, no, sir.
1 0. Yes.
1 0 becomes 0 1.
0 1.
Finally, only order is different. Both are same only, no?
Okay.
See.
Order. Okay. Both are
Because this is plus operation. Is that okay?
Yes, sir.
Yes, sir. Yes.
0 1 and 1 0, it has become 1 0 0 1. Both are same only. What about port 1?
Magnitude.
What about port 1?
1 0 0 1 5 minus.
Minus if I take outside, then it is
it
minus
becomes plus.
of the given state.
Minus 5 minus.
5 plus.
5 minus. Okay. Psi minus. Psi.
Yeah,
This is
psi
called
minus.
psi. This is pi. This is pi. Okay. Is that okay? Now stop gate, is it clear? Now,
Yes, sir.
now almost we are ready to actually move on to our topic QFT. For that, there is one more thing called DFT. First, we try to understand what is DFT. Okay. In order to understand that, first we need another thing called what are complex roots of unity. So, say omega is a complex number. Omega is a complex number. If omega n is 1, then we say that omega is complex nth root of unity. Complex nth root of unity. Is that correct? Okay, let us try to understand with example. Now, there are n complex nth roots. This equation, there are n roots. N omegas are possible. What are they? They are this omega 0, omega 1, like this. These are the roots. Okay, now n equals to 1. These are the roots. N, total n roots. Now, can you calculate for n equals to 1? What are the roots? Omega 1 equals to 1. That means what is omega? What is omega value? Simply substitute. What is n value here? N equals to 1. When n equals to 1, what are the k values? K equals to 0 to 1 minus 1. N is 1 now. K equal to 0 to 1 minus 1. That means k equals to 0 to 0. That means k equals to only 0. Is that okay? Now you substitute that value here. E power 2 pi I 0. 2 pi I 0.
By 4. By 1.
N is how much?
1.
1. Because 0 into something is what?
Everything is to be 0.
E power finally 0 into something is 0 only. E power 0. E power 0 means 1.
1.
So omega 1 is 1 means what? What is the value omega should take? 1 only. 1 power 1 only 1. There is no other way, no.
Yes, sir.
So what are complex one roots of unity?
1.
1. Is that okay?
Yes.
If you want, okay, now for better clarity, we can denote this roots as omega n0, omega n1, omega n2, total n roots. No, we denote it like this so that it will be easy. No confusion. Okay. K, this is k equals 0, k equals 1, k equals 2, k equals n minus 1, total n roots. Is that okay? Okay. Now, for n equals to 2, okay, I will show you this formula. 2 pi I k by n. Omega nk is e power 2 pi I k by n. Now you tell me what are complex second roots of unity. That means omega square equals to 1 it should become. Then what are omega values? What are omega values?
We will get I itself.
Now we simply apply in this formula n equals to 2. That means how many we get?
M is equals to 2 means
K, what are the values K takes?
0 and 1.
0 and 2 minus 1. 1. 0, 1. No? K equal to 0 is possible, K equals to 1 possible.
Yes, sir.
So that roots now we can write it like this. W20. Here this one denotes 2. This is K value. Next root is W21. Now tell me what is W20? What is W2? E power 2 pi I by 2. 0 means into 0.
0 we already know, sir.
Correct, no. That 0 only I have written. K plus 0 I have written. It is finally e power 0.
That's 1. That we already know, sir. We need to apply K is equals to 1.
This is 1.
Yes, sir.
Next.
So,
Omega 2 1.
1 is
E power 2 pi I by 2 into 1.
E power pi I.
E power
Pi I.
I pi I, right, sir? We know what is the formula for e power I theta. E power I theta is same as cos theta plus I sin theta. This is the formula for e power I theta.
yes.
Now what is this value? Cos
I.
pi plus I sin pi. What is cos pi? Cos pi is minus 1. Sin pi is 0, which is nothing but minus 1. Now that's how one root is 1, another root is minus 1. Correct? No. 1 whole square is 1. Minus 1 whole square is also 1. That means 1 minus 1, they are correct now. Is that okay?
Cos pi plus I sin pi. Sir, could you please repeat it once again, please?
Okay. So our formula is what? WNK is e power 2 pi I by n into k. Is that okay?
Yes, sir.
Now for complex second roots of unity n equals to 2. What are k values? K takes from 0 to n minus 1. Is that okay?
Yes, sir.
So k equals to 0 to 2 minus 1. That means k equal to 0 is one value, k equals to 1 is another value. Is that okay?
Sir.
Okay.
Yes, sir.
Now what are our roots? K equals to omega n. Omega n means n equals to 2. Omega 2, k equal to 0. This is one root. Is that okay?
Yes, sir. First
What omega 2? This value I substituted. N equals to 2. Same formula I substituted here. N equals to 2.
That was clear, sir. The second one.
Second one. Okay. N equals k equals to 1 I substituted here. Now this 2 gets cancelled. 1 is there. 1 into pi I is
pi I itself. E power pi I.
What is e power I theta? E power I theta is cos theta plus
I sin
theta. What is cos theta? Theta is pi, cos pi. What is sin theta? Theta is pi, it is sin pi. No matter.
Yes, sir.
What is pi means 180 degrees? No. What is cos pi? Cos pi is minus 1. Plus I times what is sin 180 is 0. 0 into I 0. Minus 1 plus 0. This is minus 1. Is that okay or any doubt?
Yes, sir. Clear.
Okay. Now, okay. Same thing can you try for complex fourth roots of unity? Now our formula is, I'll write WNK. What is WNK? E power 2 pi I by n into k. This is the formula. Now you have n equals to 4. What are k values? 0 to 4 minus 1. That means k equal to 0, 1, 2, 3.
2, 3. It will take.
So now we need to calculate W4 power 0. What is W4 power 0? Anything power 0 is 1, no. Directly.
Yes, sir.
What is this value? What is otherwise right? E power, is this okay?
We'll
2
get
by I
answer.
by 4 into 0, it is equals to 1. Is that correct?
Yes, sir.
Now can you please calculate W4 power 1?
Yes, sir.
Cos 90 plus I sin 90, sir.
Cos 90, thank you very much, sir. Cos 90 plus I sin 90. Cos 90 is 0, no, sir?
0, so I only.
I only.
I
Correct.
only, sir. I only.
Now can you please calculate omega 4 2?
Minus I we will get, sir.
Okay, I think I just directly show the answer. It will be minus 1.
Sir,
Minus
is it
1.
Okay. Yes, sir. Minus 1.
This is typing mistake. Okay.
Right.
Minus 1. What is omega 4 3?
Minus I we will get, sir.
Minus I. Now finally, what are our roots? Fourth roots of unity.
1I minus 1 and minus I.
Correct. Why? Because 1 power 4 is 1. Correct. Minus 1 power 4 is 1.
Yes, sir.
What is I power 4? I power 4 is I square into I square. What is I square? I square is minus 1. Again I square is minus 1. Again it is plus 1.
Yes, sir.
What is minus I power 4? It is 1 into I power 4. I power 4 is 1. 1 into 1 it is 1. All are giving 1 only, correct only, no?
Yes, sir.
Now is it clear what is complex nth roots of unity?
Clear.
So complex nth roots of unity, that's why we have n roots here for k equal to 0 to n minus 1. N roots. These are the n roots. Is that okay? Okay. Now, all of us know what does a polynomial mean. Okay. Now assume that this is a signal, discrete time signal. This is the value of this at the time 0. This is at the time 1. This is at the time 2. This is at the time 3. Value of that signal at the discrete times. Time 0, time 1, time 2 and time 3. 2 units, 3 units, something like that. Okay. Now this I can represent it as a polynomial. How? I'll consider it as A0, A1, A2 and like this. Polynomial of degree 3. This will be my A0. This will be my A1. This will be A2. This will be A3. Is that okay? Then I get this polynomial. No? This discrete time signal, I am able to represent that as a polynomial.
Yes, yes.
Okay. Now you can easily evaluate at a given point 6. At x equal to 6, we can evaluate now easily.
Yes, sir.
So simply substitute at x in a of x, wherever x is there, substitute 6. Then we will get this value. Now, instead of evaluating at 6, we can also evaluate this polynomial at complex fourth roots of unity. What are complex fourth roots of unity? What are complex fourth roots of unity? 1 minus 1 I minus I. I can also evaluate this polynomial at this points also. Are you there is no x, if x equals to 1, you evaluate the polynomial. X equals to -1, evaluate it. X equals to I, evaluate it. X is minus I, evaluate it. Is that okay? Then x equals to 1, we get value this. X equals to I, we get value this. X equals to -1, we get some value. X equal to minus I, we get some value. Is that okay?
Yes.
So, 1, I am evaluating given polynomial at 1i minus 1 minus I. These are complex fourth roots of unity. For me, the given thing was 2, 3, 4, 5. 2, 3, 4, 5. 2, 3, 4, 5. I am evaluating at this. I am writing the given entries as column. Then I am getting something. What is that? 14 minus 2 minus 2i minus 2 minus 2 plus 2i.
Plus y.
Okay. Now this I will not show you. Okay. Now I am talking about an operation which transforms this to this. This input 1 to this output 1. And that operation is nothing but discrete Fourier transform. Okay. Okay, now we talk about that in detail. Now all of us know what is a discrete signal. It is a signal whose values are known at discrete points. No? Like earlier I have shown xn equals to like this. Only this discrete points I know what is the value of that signal. Other points it is undefined. It is not like continuous signal like this. If I take 0, here some value is there. 1, this value is 2. That means the point is like this. In between, it doesn't exist. Is that okay? Now I am talking about discrete signal. That means it is defined at only specific distinct points in time. What are those points denote? They represent amplitudes, signal strength, amplitude at that instant. Okay. Now, this is a time input is time domain. At 0th time, 1, 2 units, what are the values? That I can consider it is a time domain. Okay. Now, this is a signal. I can represent it signal, discrete time signal like this, x of t. T is 0, it is defined. X of t is defined. T equals to 1, x of t is defined. T equals to 2, x of 2 is defined. And so on, t equals n minus 1, that value is defined. And that value is called amplitude of that signal. For example, x of 3. If x of 3 is 10, what does this 10 denote? At the third unit of time, what is the strength amplitude of that signal? That value denotes. What is discrete signal? Is it clear?
So discrete signal is a superposition of qubits, sir. Qubits.
No qubits, nothing. Simply I am talking about discrete signal. That's all. No qubit, no quantum part yet.
No basic. Oh, okay.
What general digital signal processing we call it as what is discrete signal. Okay, this is discrete signal. Now, in this discrete signal, we show amplitudes at different instances. No, different instances. But I want that time series that amplitudes to frequencies. For that, we use Fourier analysis. Our signal is in time domain. Now I want it in frequency domain. Okay, so for that we use Fourier analysis. We have a signal in time domain. We are converting it into frequency domain. For that Fourier analysis is used. Okay. Then what is discrete Fourier transform? What is discrete Fourier transform? Now, see, A0, A1, and so on, An minus 1. A0, A1, and so on, An minus 1. These are at time 0 signal amplitude, at time 1 signal amplitude, at time unit 2, these are signal amplitudes, let us say. Then how to find its equivalent in the frequency domain? It is given by y0. This let us call it as y0, y1, y2, and so on, yn minus 1. Yn minus 1. How to get this y0? How to get y0? You consider this as a polynomial like I mentioned earlier. Then evaluate it at the complex nth roots of unity. Then automatically we will get. For example, here what is that we have done? This is, for example, 2, 3, 4, 5 is our signal. Okay, this time signal, time domain. That 2, 3, 4, 5, I have written it as a polynomial like this. Polynomial like this. Then I am evaluating that polynomial at point 6. Instead of at x equal to 6, I can also evaluate it as complex fourth roots of unity. Also, I can evaluate that polynomial. Okay. Now, input is 2, 3, 4, 5. Output is 14 minus 2 minus 2i minus 2 minus 2 plus 2i. So for that, I need to do some operation here. No, that operation is nothing but discrete Fourier transform. Are you getting me?
Yes, sir. Please continue.
Okay, it will be more clear once we. So this is an operation. So these are, again, you can see these are simply evaluating that polynomial. So in general, this is the polynomial given to us. We are going to evaluate that polynomial at complex nth roots of unity. Wn0, Wn1, omega n minus 1. We evaluate it, and whatever we get, those values are wise. This wise sequence only we call it as discrete Fourier transform. This one is nothing but omega n0. This is omega n1. Okay. Okay, no, that's what I have shown this. No, that only we call it a discrete Fourier transform. This wise whatever we have got, this is called discrete Fourier transform. Evaluating this at given complex nth roots of unity for given n. Here n equals to 4, complex fourth roots of unity we evaluated. This entire thing we can represent it as linear transformation like this. Input values, let us call it as x, vector x, or matrix x, or column vector, column matrix x. Output, whatever we got, let us call this as y. Then there is someone here who is changing this x to y. No, we changing this x to y. That is nothing but an operation. That operation is discrete Fourier transform. This matrix we use so that this will change it to this. Like RMR matrix we use. Like that, different matrices we use, they change input to output. No, inputs quantum sequence to output. But here, both all are classical. All are classical. This input sequence we have got this sequence. This sequence. Now, if you look at here, what is this matrix? If you observe here, first row is Wn power 0 whole power 0. First root of that Wn power 0 whole power 1 and so on Wn power 0 whole power n minus 1. This is first row. What is Wn power 0 whole power 0? 1. What is Wn power 0 whole power 1? 1. All are ones. That is first row. Then what is second row? What is second root? Wn power 1. Again, this second row is Wn power 1 whole power 0, Wn power 1 whole power 1, Wn power 1 whole power 2, and so on Wn power 1 whole power n minus 1. This is our second row. Is that okay? This is first root evaluation, second root evaluation, third root evaluation, last nth root evaluation. How we got this matrix? Is it clear?
Yes, sir.
What are complex? Okay, anyhow, we have specific examples. Can you calculate what is DFT of 4?
This, right. Fourier transformation of Fourier.
Whole power 0, omega 4 whole power 1, omega 4 0 whole power. Hello? Hello?
Sir, yes, sir, we can hear you. Sir.
Okay. Now, what is DFT for? Discrete Fourier transform 4. This is the one. Second row is nothing but second root evaluation. That is W4 power 1 whole power 0, W4 power 1 whole power 1, W4 power 1 whole square, W4 power 1 whole cube. Okay. Now you can see here, no same thing. Next, the third one is next root W4 square. W4 square whole power 0, W4 2 whole power 1, W4 2 whole square, W4 2 whole cube. Okay. Next, to fourth one. What is fourth one? Can you tell me what is fourth one? What is fourth one? Fourth row.
W4 3 power 0.
Thank you, sir. Next.
W4 power 3 power 1.
1.
Power 2 power 3.
Is that correct? Now this is something power 0 is 1. No, that's why this entry is 1, this entry is 1, this entry is 1, this entry is 1. First row is 1. Here, this is also power 0. This is also 1. W4 power 1. 1 into 1, 1. 1 whether we write or not, same thing. What about this one? 1 into 2, 2. W4 2. Next one is W4 3. Next one is
1.
Power 0 means it is 1. Next one is 4 2 power 1. 2 into 1 1. 2 into 1 2. That's why this 2. 2 into 2 4. That's why this 4. 2 into 3 6. That's why this 6. This is again 1 4 3 power 1. 1 into 3 3. 2 into 3 6. 3 into 3 9. Is that okay?
Yes,
is that okay?
Yes, sir.
Now, if we simplify this, we'll get this matrix. That's all. We'll get this matrix. Now, we calculate it using this matrix. The same values 2, 3, 4, 5. Earlier we discussed now. Polynomial evaluation 2, 3, 4, 5. And what are the final values? 14. These are our final values. Now we calculate it using this method. Again, same values we got. Same values we got. This is our DFT. Is that okay? Matrix. And this sequence it is called DFT. This is frequency DFT. Is that okay? Is that okay?
Sir, what is the right hand side, sir?
Right hand side, that is very values. First one is time domain, second one is frequency domain. And the matrix, that transformation is that matrix.
Okay, sir. Okay, sir. Thank you, sir.
So Fourier analysis, that is for time domain to frequency domain conversion, no?
Got it, sir. Got it.
Okay. Now the same thing we extend to quantum. Okay, no? Now, what is QFT? It is quantum implementation of DFT. Now we know what is DFT?
Discrete.
Discrete Fourier transform. How it works, all those things, it is clear, no? Okay. It is okay. Now, similar to DFT, here all quantum operations are unitary matrices. That means they are represented by unitary operators. They are represented by unitary matrices. Is that okay? And this QFT, we can implement it as algorithm, or we can consider it as algorithm or circuit also. We can also implement it as circuit. I will show you that circuit also. Now, you observe that after completing this QFT, you observe that it is a generalization of Hadamard transform. You understand this point. Okay, now these things will be clear after completion of QFT. Okay. Okay. Now, at least now, is it clear to you? QFT is also one matrix. Similar to DFT, is it a matrix or not?
Yes, sir. It's a matrix. Yes.
It's a matrix. Because this is a quantum operation, input must be some quantum state, output also must be quantum state. Is that okay? So it is a matrix which takes one quantum state as input and gives another quantum state as output. Is that okay? This QFT, it is an operation which takes some quantum state as input and gives another quantum state as output. You agree? Now, what is this QFT? Okay, now what is this QFT? So it is similar to, it is given by this matrix, U11 n by n matrix. No, this is a matrix. This is input quantum state. This is output quantum state. Input quantum state, we are applying some operation here. Then we will get output quantum state. This no time you understand this matrix. No time to understand this matrix. Okay, let us see. This is n by n matrix. That means what does it contain? What is each entry here? What is each entry here? What is first entry? We are evaluating it at a complex nth roots of unity. What are our roots now? We are using capital N notation here. And swan W, N, N minus 1. These are our roots now. These are our roots. Is that okay?
Okay, sir.
These are our roots.
Sir,
now,
sir, yes.
what is first to know? What is first to know? First
Sir,
to know is Wn0 whole power 0, Wn0 whole power 1, understand Wn0 whole power n minus 1. Is that okay?
Sir, a small
What
confusion for me.
Tell me, sir.
Sir, it was said it is an operation, right, sir? This
It is an
QFT.
operation.
Is that operation we are representing by using this matrix? I am little confused here, sir.
Tell me, sir.
This one is a matrix, no, sir?
This is matrix. Here I have not shown actual values. This is the general template. Now we need to fill the values here.
No, actually in the definition it was mentioned as an operation, right, sir?
It is an operation. Operation is represented matrix only, no, sir. All quantum operations are unitary matrices.
Okay, okay, sir. Okay, sir. Thank you, sir. Thank you.
Like Harmad operation, this is also one operation. That's all.
Okay, sir. Okay, sir. Thank you, sir. Thank you.
Okay. Is that okay? First row, is it clear, sir? Now can you tell me what is second row?
Wn1 whole power 0.
Wn1 whole power 1 and so on.
Wn
power 1
whole power
n minus 1. Finally, what is last row? What is last row?
Last row is about n now, sir. N1.
Wn n minus 1 whole power 0. Wn n minus 1 whole power 1 and so on. Wn n minus 1 times n minus 1. N minus 1.
Hello?
Hello, madam. Now is this okay now? Hello?
Yes, sir.
Okay. Now, here this is normalization factor to satisfy that mod alpha square plus that unitary matrix, no, that definition. Okay, now we put this 1 by root n.
Hello, sir. Hello.
Now the screen is visible, no, madam?
Sir, in middle your voice is not clear.
Now.
Now it's visible, sir.
Okay. Thank you, sir. Thank you.
Okay.
So this is the matrix. Is this okay, or any doubt in this? How we got this? First row is using first root. Second row using second root. And the nth row, last row using nth root. Is that okay?
Sir, here U means unitary operator, right?
This U is only for notation purpose. This matrix is unitary matrix. For that intention, with that in mind, it is written as U. That's all. The actual matrix is this, which is shown in blue in color.
Yeah, okay, sir.
This is simply in matrix A means we write A11, A12, A21, A22. No, madam. A 2 by 2 matrix we write A as like this. No.
Yes, sir.
This n by n matrix I have written like this. Now I am explicitly saying what is U11, what is U12. Those values I have mentioned here. Is that okay?
Right, sir.
Okay. Now we have already seen what are complex first roots of unity. No. Okay, no? N equals to 1. What are the answer? Omega n is 1 means we know that omega must be
1 and 2.
1 only. Now can you write DFT of 1? Can you write DFT of 1? What is this matrix? 1 by root n.
1 by root n means.
N is 1. Okay. N is 1. 1 by root 1. Next. What are roots? Only one root, no? Omega n power 0. It should go up to omega n power n minus 1. N minus 1 means 1 minus 1, it is 0. Up to 0 only. That's all. No other roots. If you simplify this, how much you have got? This is 1.
0 is 1 only.
1 only. Is this okay? Is this okay?
Yes, sir.
Okay. Now Q of T2. We know what are complex second roots of unity. Okay, no complex second roots of unity. Now can you please calculate what is Q of T2? Q of T2. What is Q of T2? It is
1 by square root.
omega 2 0. First root is omega 2 power 0. N is 2. That means n minus 1 is 1. That means if you look at our previous matrix, it will go up to n minus 1. No, for each root, it will go up to 0 to n minus 1. So omega 2 power 0 first root, whole power 0 to omega 2 power 0 whole power n minus 1 is 1. That's all. Next, this we forgot. 1 by root n, 1 by root 2. Okay, 1 by root 2. Now, what is next root? What is next root? What is next root? What is next root?
W2 power
What is
W2
next?
1 W2 1 power 0.
W2 1 power 0. Thank you very much, sir. Next.
W2 1 power 1.
Thank you, sir. So now if we simplify this, 1 by root 2, 1 by root 2 times. What is power 0? Power 0 means it is 1. 0 into 1, 0. This is also 1. This is also 1. What about this? Omega 2, 1 into 1, 1. What is omega 2, 1?
Minus.
We have already calculated, no?
Minus
Omega 2, 1 is minus 1. So this is minus 1, which is same as 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. This 1 by root 2, I am taking it inside. Is it okay? 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. Is that correct? What is this? Which is nothing but same as Hadamard transform, no?
Yes, sir. Yes, sir.
Q of T of 2 is nothing but Hadamard transform only.
Same we are getting here also.
That's what. Now you will understand later why Q of T is generalization of Hadamard transform. Now at least partially you might have understood. Okay. Now can you please calculate Q of T4? Okay, Q of T3. Q of T3. Roots are already shown here. 3 roots. 3 roots are given here, no, already. What is Q of T3?
Here.
What is Q of T3? What is Q of T3? 1 by root 3. W3 0 whole power 0. N is 3. N minus 1 means up to 2 we should go. W3 0 1. W3 0 2. Next root is W3 1 0. W3 1 1. W3 1 2. Next root is W3 2 0. W3 2 1. W3 2 2. Is that okay? Is that okay? Is that okay?
Yes, sir. 1.
See, first row and first column are ones, no?
1. Yes, sir. Yes, sir.
W31 also, this value we know. Okay, anyhow, we have calculated those values. So these are the things, no? That's what we have written. No, it
Yes,
is
sir.
only simplification. It is only simplification. After simplifying, we got this. Is that okay? Now QFT4, can you please? We have already done that. QFT4 entire matrix you should be able to calculate. QFT4. What are roots? What are roots?
What the roots of unit is?
1 minus 1, I minus I, they are the roots, no. But order is this. 1I minus 1 minus I. This is order is important. Okay. Now QFT4, can you please calculate? Hello, madam. Monica, madam.
Hello, sir. Tell me, sir.
Okay, sir. If you permit me, I can extend to some more time because we started bit late. Okay, to complete this topic.
Yes, sir. Yes, sir.
Okay. Okay. Thank you, sir. So, are you calculating QFT4?
1/2.
Okay. I display the answer, sir. Is this okay, sir? Omega 4 0 power 0 0 1 2 3. Next row is next root. Next row is next root. Last row is last root.
Yes, sir.
Is that okay?
Yes, sir. Yes, sir.
Sir,
Okay.
it is also like 1 0 0. To be 1 0.
Okay. Maybe if you are familiar with the procedure, we can proceed. Procedure
Yes,
is
sir.
this. Later we can
Yes.
calculate values. No, that is not difficult. Okay.
Okay, sir. Okay.
Okay. Now, similarly, complex 8 roots of unity means there will be 8 values. Okay, no? They are denoted as.
Sir, is there any shortcut forms to calculate fast? Because it is taking much time to calculate. So need to do practice more.
Because those are using. Because we need to use G power I theta formula also, complex numbers also, it is bit difficult, madam.
And
Okay.
moreover, this next time, if we calculate also, it will take more time. So it's
More
better, sir, it's better to continue tomorrow to in depth so that we can understand in a proper way. Or else kindly provide this material to us, sir.
Okay. No, I'm not stopping now. Okay.
Okay.
I'm not. I will complete it. Okay. You don't worry.
Right.
Okay. I'm not closing now. I will show
Sir,
you.
I request you to kindly send the material also, please.
Okay, madam. Okay.
Right.
Okay. Okay. Similarly, complex 8 roots of unity we can calculate. So these are the 8 roots. 8 roots. We need to spend some time to actually do it. And QFT of 8, it is 8 by 8 matrix. Is that okay? Up to this part, is that okay? Now we try to calculate. We have understood what are the matrices. So now this operation operates on how many qubits? It is 8 by 8 matrix. So it operates on how many qubits?
2 power 3.
3 qubits. Sir.
3 qubit.
Yes, sir.
So input should be 3. A quantum state with 3 qubits here. Here what is input? In this case, this is 2 square by 2 square. No. What is input? A
2
quantum
qubits.
state with
2 qubits.
2 qubits. 2 qubits. Okay. Now, can you please calculate T2 of ket 0? We know what is Q of T of 2. What is Q of T2? It is same as
Hadamard.
Hadamard. What is Hadamard? This is Hadamard, no?
Yes, sir. Yes, sir.
Now Q of T2 of ket 0, you please calculate.
QFTT of ket 0.
Same thing. Ket 0 is 1 0. Q of T of 2 is that matrix. Ket 0 is 1 0. After that, it is normal multiplication. No.
1 by 2 of all ones 4 row and column.
1 by root 2, no, madam.
Yes, sir.
So it is same as we calculated earlier when we talked about Hadamard operation. It is 1 by root 2 ket 0 plus 1 by root 2 ket 1.
Ket 0 plus ket 1.
Q of T2 of ket 1. Same thing, in place of 1 0, we need to write. In place of 1 0, we need to write
0 1.
0 1. That's all. So if we simplify, we will get 1 by root 2 ket 0 minus 1 by root 2 ket 1. Is that okay? Now, similarly, we try to calculate. This is another way of calculating. Okay, now this is matrix form we have given. This is another way of calculating. This is the actual formula for QFT. Okay, now this is in Dirac notation, either matrix form or Dirac notation. Both Dirac notation is either compact form. Matrix means it is a lengthy matrix we need to write. Same thing we can represent in terms like this. So if you substitute values here, j equal to 0, again same thing we are getting. In that summation, if you substitute j equal to 0, we are getting 1 by root 2 ket 0 plus 1 by root 2 ket 1. J equals to 1, whatever we calculated earlier, same thing, 1 by root 2 ket 0 minus 1 by root 2 ket 1. Okay. Similarly, these are the values we got. Okay. If you simplify that, it will be, what is this? What is first one? What is first one? It should be 1 by root 2. First one should be 1 by root 2.
1 by root 2 get 0 plus e power.
1 by root 2 ket 1. Second one is 1 by root 2 ket 0 after simplification. This we have already calculated, no? Using other method we calculated, no? This two we have already calculated. See, here we calculated, no? Same answers. This is direct method. This is the Q of T is given in Dirac notation. That's all. Okay. Now similarly Q of T. Okay. Q of T 4 of ket 0. This is Q of T4. Q of T4 of ket 0.
Sir, is that get 0 or get 0 0?
0 we can write it as 0 0, no madam. Both are same, no. Why? Because to say that this is decimal form. Let us say this is decimal. In binary, 0 is 0, 0, because I am talking about 2 qubits now here. I am talking about 2 qubits.
Yes.
Are you getting? That's why I have explicitly written it as 0, 0. While substituting here, this is again decimal, madam. This is decimal. 0, 0 means 2 zeros we should not put. Only 1 0 we put. Okay. So now using this easily we can calculate what is this. QFT4 is this. What is KT00 matrix for KT00? That we already discussed. No. What is matrix for KT00?
1 triple 0, sir.
1 triple 0. Thank you very much, sir. Now if you multiply whatever answer we get, that is the QFT4 of KT00. Is that okay? Similarly, we can calculate QFT4 of KT01. What is KT01?
1 is.
No.
Get 0, 1. Get 0, 1 means?
What is KT01?
0 1 0 1 0 0.
Ah, thank you very much, sir. 0 1 0 0. Again, after multiplying, we got this. Similarly, what is KT10?
0 0 1 0, sir.
0 0 1 0. Multiply with that. This is the answer. Finally, KT11. What is KT11?
0 0 1.
0 0 1. QFT4 is this 0 0 1. Multiply. We get this. Is that okay? Is that correct? Okay. Now similarly QFT, if you are asked to calculate something like this, you are given n equals to 4, but for this input sequence, you are for this quantum state, input state, you are asked to find QFT. Okay. So KT0 means, how to write this? 1 is 0 1, 0 is 0 0, 2 is 1 0, 3 is 1 1. So KT00 is 1 triple 0. KT01 is 0 1 double 0. KT10 is 0 0 1 0.
1 0.
KT11 is
0 0 0 1.
If we add all these 4, we will get this. Because if I add now first position 1, here second position 1, here third position, here fourth position. If we add all positions, we will get 1 no.
Exactly.
Okay. Now QFT of that. So here 2 qubits. So I am using QFT4. This is 2 qubits. Now what is F? F is 1 by 2, that 4 ones. Again multiply whatever we get, that is final answer. Finally we got 1 by 4 of KT00. Is that okay? This you can tell G. What is G? G is KT0. So KT0, how to write this? This is 2 by 2 matrix, a 4 by 4 matrix, 2 qubits. 0 means it should be 0 0.
0
0 0 means 1 triple 0. Is that okay?
Yes, sir.
Okay. Next.
Get 1 means H. 0 1.
0 1. Thank you.
Hello?
Madam, please. Completed? Is that okay?
Yes, sir.
0100. Okay. Okay. Now find the QFT of 101. 101 means 3 qubits. 3 qubits means 8 by 8 matrix, no?
Yes, sir. Got
This is QFT 8. How to find this? How to find this? 101 means what?
It is 5. So 0,
5 means 000
0,
of
4
4
zeros, 1
zeros, 1, 5 zeros, 1 00. Is that okay? After that, it is multiplication. The clue is if there is only 1, after multiplying, answer will be the corresponding column. This is 6th position. No, this column will be the answer. Same
Sir, come
thing.
again, please.
Huh?
Hello, sir. Hello,
Ah,
sir.
madam.
Repeat the same again.
Because here there is only 1. If you are multiplying with column vectors with only one position, all zeros, answer will be wherever 1 is there, that column in the first matrix. That will be the answer. Here answer is 1 by root 8 into this column. Is that okay?
So this is what a trick.
Is that okay now? Okay. Now again we can, this is matrix form, we can convert into Dirac notation. 1 means it is 0 0 0, this is top, this is 0 0 1 amplitude, this is 0 1 0 amplitude, like that if you write, then finally we will get this. Okay. Okay.
Yes, sir.
Now the same thing we can implement using this circuit. Using this circuit, this is the QFT4 circuit. This is called controlled phase operation. This we discuss now. What happens here? Ket 0 is input me. Only ket 1, this becomes e power I theta. Theta is how much? Pi by 2. E power I pi by 2, ket 1. In all other cases, no change. Same. Okay. This is swap gate. Now you can apply first qubit, you can apply Harman gate. After that, if you are familiar with quantum circuits, you can complete this without any difficulty. And check whether the same answer we got or not. For this, for example, this is QFT4 of 0 0. This we have already calculated using matrix method. Using this method also you calculate and check whether you are getting the same answer or not. Is this okay? Okay, similarly, for this also you can try and compare. This also you can try. This also you can try. This is for QFT4 circuit. Next QFT8. This is a circuit. Here also you can try for 5. We have already done for 5 now using matrix method 101. Here also you can do that. And now you please note down this for assignment. Calculate QFT 4 ket 01. This you calculate 1. Second one, calculate Harman tensor Harman. This is third one. Determine the following. Next, determine what is 1 ket 1 tensor ket 1 tensor ket 0. What is this? This also you please find out. Okay, these 3 you please do it. Okay, na? This is for assignment. If possible, you can also try this depending on the time. QFT 8 of ket 110. Ket 110. This takes lot of time. Okay, you all of you note down this code. This is for assignment. Okay. Now, so these are the differences between DFT and QFT. DFT classical sequence, here it is a quantum state. So here x's are transformed to y, here quantum state to another quantum state. Here formula is this, here this is the formula that we have already seen. So for DFT calculation, there is very nice algorithm classically that is called fast Fourier transform. It is a divide and conquer algorithm which runs in n log n time. But this quantum, it is very good. This takes order of n log n squared quantum gates. Okay. And finally, what is that we have discussed in this lecture? We have started with qubit. What is general form of qubit? Alpha ket 0 plus beta ket 1. Here, what is the condition? Mod alpha square plus mod beta square is 1. What is tensor product of ket 0 with ket 1? What is tensor product of ket 0 means 1 0. Ket 1 is 0 1. If we multiply, what is that we get? What is that we get? 0 1 0 0. This is the tensor product. Next, we talked about Hadamard. This is different quantum operations which are required to understand QFT. Next, evaluation of polynomial at a complex for nth roots of unity. N equal to 2, what are the roots? 1 and minus 1. N equal to 4, what are the roots?
1 I minus 1 minus I.
Minus 1 minus I. For different n values, you can try. Then what does discrete signal mean? Then what is DFT? What is QFT? These things we try to understand. Okay. And these are some of the references. Thank you. Sorry for extending it because I started a bit late. I could not complete. That's why I extended a bit late.
Oh, sir, thank you so much for your question.
Thank you, madam. Thank you. If there are any questions, okay. Otherwise, I'll just leave the meeting. Okay.
Oh, sir, we want that we add a video or notes, sir.
That you please ask them, madam, the concerned in charges.
Okay,
Okay,
sir.
okay, okay. Thank you, madam.
Thank you.
Okay, if there are no doubts, then I just leave the meet. Thank you very much for being interactive. Okay, thank you once again.
ఎంత కొంత వేసుకోండి ఏదో ఒకటి కానీ ఇంటికి ఉంటుంది ట్యాబ్లెట్